Okay, so I think you should see my screen in a moment. I'll make it full screen. So we are looking at this um, concept of doing substitutions in a lambda calculus term. And um, so one thing I happen to mention is substitution can fail in very intricate ways. And instead of looking at the final solution where you won't understand how we came to this final solution, it is better to sort of go with the intuitive development of a solution, and we'll sort of see how it breaks, and then we'll finally arrive at the right solution. Right. So our take one was this particular substitution method, and the interesting bit is what we did for abstractions. For abstractions, lambda y dot t1, if you want to substitute s for x, then we said naively go ahead and then continue substitution for the body of the abstraction, right? So if you want to substitute in an abstraction, just recursively call the substitution in the body. Right? The problem here is that um, imagine that the abstraction that you're substituting in is this identity function lambda xx, right? And you're replacing all uses of xs with y, right? And the important qualification that I sort of missed there is all free uses of x's, right? You should only, so when you think of substitution, you're only substituting for free occurrences of x. What happens when you substitute for bound occurrences? The meaning of the function changes, right? Abstractly, what it means is um, if I replace x with y in this function, this constant function becomes, sorry, this identity function becomes the constant function, right? These two are not alpha equivalent, for example. And I mean, this happens to be an identity function. In OCaml, this would be a function that always returns, say, 0 and ignores the argument, right? And this is not what we want. This is sort of breaking the meaning of substitution. So we said, alternatively, we will try to go with this definition, right? Where if the variable being substituted is the same as the binder, then don't do any substitution, because any occurrences of x within T1 is bound to this x, the binder. So of course you shouldn't do the substitution. So we will just return the same abstraction as before. If they are different, right? I'm explicitly qualifying that x and y are different. Then recursively go ahead and do the substitution within the body. At this point, you can sort of look at the shape of this failure, right? The identity function has become a constant function. So you can also ask whether there is a case for a constant function to become an identity function. And that is precisely the failure that we will have here, right? And again, the take two is also not right. Observe that there is a constant function here, right? Which is, it takes any argument x and then returns y. In OCaml, you can just think about this as taking some argument and returning 0 or 1 or some constant, right? So it doesn't matter what the input is, it is always going to return y. If you replace the occurrences of y with x, what happens is this x is now captured by this binder, right? So we call this getting captured. Why is it getting captured? This x is not referring to this binder at all, right? This x is sort of something else that is outside. But because we use the same binder name, x here, this constant function, right? If you do the substitution where you replace x for y in this term, we get lambda xx, which is an identity function. So the problem here is the constant function, this function has become an identity function because of the substitution. This is not what we want. We are changing the meaning of what the function is, right? So the precise problem here is that the free x in the term that you're substituting, right? There is a free x here, but you can imagine this to be a large term as well. Some x plus x or x minus x, some involving lambda with a free x, right? That term, that free x in that term is getting captured by this binder x, right? the free variable here, X, is getting captured by the binder, right? And that's the problem here. We can try to fix this problem, right? If you sort of compare take 2 versus take 3, all I've done is I've added another clause here, right? Where I say, and make sure that when you replace for X, right, in T1, make sure that the term that you're substituting, right, does not have a free variable, which happens to be Y. So the binder is not a free variable in S. And the idea and the reason why we put this restriction is that if you do the substitution, you will have the undesirable property that this whatever free variable that you had in S gets captured by this binder, right? The meaning of the term sort of changes. And what happens when you add this restriction? The problem is that the substitution is no longer a total function. What are total functions? Total functions are functions where the range is defined for all of the entirety of the domain, right? So, but unfortunately, this substitution description that we have here is not total, because exactly the example that we saw in the previous slide, right? Here is a constant function. I'm substituting x for y in this constant function, and the rule here says that x shouldn't be a free variable in the term that we are substituting. It is a free variable, right? This is bad. So if you use this procedure and give this particular function and the substitutions as input, this function will get stuck. It will just say, I don't know what to do with this, right? So how can we fix this? So the way we fix this is by adding a new rule. Okay, so bear with me. This is the last one. We've got this right, but just bear with me. So what we are doing is we had all the rules except this additional rule in take 3. What does the last rule say? So it captures the final case, right? If x is not equal to y, the variable that you're substituting is not the same as the binder, right? And y is a free variable of s. Y happens to be a free variable in s. The problem here is, as I mentioned, when you do the substitution, there is a chance that the free y's in s will get captured by this binder y. In order to avoid the capturing, what we can do is we can apply renaming, right? Just the substitution that we are defining now. What we do is instead of just leaving this as y, we rename it to w. We refactor this function as w, and in T1, wherever you find y, we substitute that with w. So we are actually doing first one renaming, where we sort of take y and replace all uses of y with this fresh w, right? It is important that w is fresh. You can sort of intuitively understand freshness as this this variable name has not been used anywhere, right? That's the definition of freshness. So take a fresh variable name. So you can create a new variable name and make sure that that variable name is not used anywhere else. First, do this one step of renaming, right? So first, rename this term such that lambda y dot t1 becomes lambda w dot t1, where all occurrences of y, the free y's, are replaced with w. That is what this says, right? Once you do that, then we can always apply this rule, right? We know for a fact that w is fresh, so w cannot be part of the free variable set in S. Then the definition of freshness would be wrong, right? So we know because w is fresh, w will not be part of the free variable set of S, so this rule can apply, and we can go ahead and perform the substitution. Okay, it's a bit intricate, but I hope that these examples, I recommend you to go through the two examples, right? This constant function being identity function and identity function being a constant function. So just keep those in mind and slowly work through the substitution. You will understand how it works. In fact, substitution happens to be one of the subtle points of lambda calculus, even today, right? Even programming language experts get confounded by this. And what programming language researchers try to do is to prove that substitution is right according to some specification. And the proof usually gets very difficult, especially in the substitution in the case of abstractions. It's a constant problem. So if you feel that this is difficult, you can take refuge in the fact that even programming language researchers feel that this is difficult, right? So it's not just you. So okay, so we have this. What can we do with this? Now our example actually works out, right? So here is the example that sort of got stuck in the previous state. So what are we doing? We are substituting x for y in this constant function, which always returns y. Because x is part of the free variable set in the substitution term, which is just plain x here, we first replace all occurrences of x with some fresh w, right? So what this happens is you replace lambda x dot y to lambda w dot y, right? And then perform the substitution. So what are we saying? We are saying that wherever there is a y, replace that with x, so that becomes x. Now observe that the meaning is sort of preserved, right? So this ignores x, right? That ignores x and always returns y. And what the substitution is saying is wherever you return y, return x, right? That is what the substitution is saying. And we achieved this by renaming first. We renamed x to a w and then did the substitution, which got us the desired semantics. Okay. Again, it is okay if you don't understand it as I explain it now. Go through these set of slides, but also read through Types and Programming Languages book, the particular chapter I referred to in the schedule, right? So if you want more material, you can refer to that. Once you get it, it'll be fine, right? So I don't know, it might just take a little bit of time for you to wrap your head around it. But what I do have is a implementation of substitution function, right? So if you want to play around with a lot of examples, see how the substitution works. That is how I sort of understand these things. You can play around with the substitute function. Let me clear the output so that I don't give away all of the tricks. Please start that clear out. And I will need to do this. Okay, so going back to this slide. Okay. What did I do? Oh, I did restart and run all. Okay. I was very surprised why clear all did not clear everything. Okay, so now I have the right setup. So what I wanted to take away is there is an implementation of a substitute function, right? Which I'm applying on the same examples that we saw on the previous 3 slides, right? This is the first easy example where we are substituting. So it takes 3 arguments, right? I mean, we are using different syntax, so it might be worthwhile to explain what we're doing. This is the term that we are substituting in, right? This is the variable for which we are substituting, and this is the term we are this is the term we are actually substituting. Let me screw it up. Okay, let me try again. This is the term that we are substituting in, right? This is the variable, and this is the term that we are substituting with. Okay, now it's better. So we are replacing the occurrences of x in this term with this lambda z dot zw. And if you do that, you get lambda y, lambda z dot zw, because x has been replaced by this, right? So here I am replacing the free occurrence of x's with y. And the observation is that there are no free occurrences. This x happens to be bound to the x here. So the output will be lambda xx. So this is the example that we saw just earlier. And this is the last example where you have a constant function, right, which always returns y. and I'm replacing the occurrences of y with x. And the observation is that the meaning has to be preserved. So if you naively replace it, you will return an identity function. So we first do the renaming and then do the substitution. So what you end up having is a new variable. I'm not using w here. It sort of generates a number and then creates freshness through that. So you have a new variable called x0, which returns x, right? So, but anyway, x0 is ignored, just like the original function, right? X is ignored here, just returns y. Here, x0 is ignored and returns x. So, what you will do in your assignment 2 is implement substitution. Okay, so you will. I have an implementation of substitution. You will also implement a version of substitution yourself. The only thing to do is to take this function, right? This is sort of a specification, but it's also you can sort of read it as a function that takes one argument, right? Just like this. The first argument, the second and third argument. So there is the first argument, second and third argument, and you have to return some value. There is a recursive call, right? You can sort of look at these as recursive calls. These as just conditionals, right? Conditionals for applying the recursive calls. And if you directly sort of translate this take 4 into a OCaml function, you will arrive at what I have here. So what I'm sort of hoping that you will learn in this is how do you take specifications like this, which you find in any domain, right? You might have lots of domains where you want to do some sort of specifications that are defined here, convert that to a function. And functional programming languages sort of give you a lightweight way of encoding some of this, because you can stick to the notations as close as possible, right? And you will see that your implementation will be very close to the definition that I have here. Okay, so we've defined substitution. If you can recall from the last class, the reason why we studied substitution was to formally define alpha equivalence, right? What is alpha equivalence? Alpha equivalence is I have two lambda terms that are that I can call equal if I can get from one term to the other just by renaming, right? And in order to define renaming, we define substitutions. Okay, so it's sort of a circuitous thing, but now that we have defined substitutions, we can easily define alpha equivalence. So there are three rules, and the reason for existence of three rules is we have three production rules in lambda calculus, right? So there is a variable rule, there is an application rule, and an abstraction rule. This is a variable rule, this is an application rule, and this is an abstraction rule. As I introduced while introducing expressions, if expressions, this sort of writing down rules is known as writing down inference rules. Again, just to recall, so you will have a bunch of premises on the top. So this is one premise, this is a second premise, sorry. This is the second premise, right? You can have multiple premises on the top, and this is the conclusion, right? This is what we are concluding, assuming that these premises hold. So writing down inference rules is a very standard way of expressing formally the properties that you want. And in programming languages, we tend to use this often. So I'm sticking to this inference rule setting. It'll come in very handy when we look at other things later. So what does this easy rule say? It says that there are no premises, right? And it just says that the variable x is alpha equivalent to variable x, right? This should be obvious. So if you have a variable x, and if you give me variable x, then they are the same variable. These two lambda terms are alpha equivalent. What is alpha equivalence for applications? It says that m applied to n is alpha equivalent to m prime applied to n prime if m is alpha equivalent to m prime and n is alpha equivalent to n prime. So you recursively just call alpha equivalence on each of the subterms in the application. And finally, how do you describe alpha equivalence for abstraction? So this is why we had defined substitutions. I can say that lambda x dot m is alpha equivalent to lambda y dot n, right? When can I say that? I can say that, what do I intuitively need to do, right? I need to say, pick a variable name, right? Pick some variable name, which is z, rename all x's in this term, like free occurrences of x's in this term with z, so that everything is in z instead of x. Similarly, pick an occurrence, rename all occurrences of y in n with z and replace that with z. So we sort of rename the variables to a common variable name. Now, if these two terms are alpha equivalent, then we know that the original terms are alpha equivalent. This is what we're doing, right? So, so how do we do this? So we want to pick this fresh variable name, right? So that we are not in conflict with any of the other variable names that are used. In particular, there could be free variables, right? If you pick a variable name which happens to be a free variable, that gets bound. This is the constant problem all the time. So we pick some z, right? We pick some z, which is not an element of the either the free variable of m or the free variable of n, right? It is not a free variable in the set that is obtained by the union of m and n, right? It's a free variable. I could have equivalently written it as z is fresh. Just pick a fresh variable, right? Replace all occurrences of x in n with z, and similarly replace all occurrences of y in n with z, right? So what you're doing is, we want to rename the body of the function such that they all use z now. So that is what we are using substitution to express, right? We are using this capture avoiding substitution, right? So to express that fact, once you rename all the variables, now if they are alpha equivalent, then the original term is alpha equivalent. This original term is alpha equivalent, right? So that's the way you have to read these inference rules. So you sort of say, start from here, right? And then this will have some terms here which are used in the premises. So then follow along the premises from left to right. And once you reach the end, then you can say, okay, assuming all of this holds, then the conclusion holds, right? So we've defined alpha equivalence. I suspect that you have to implement alpha equivalence as well in assignment 2. Yeah, I think so. Okay. So alpha equivalence is a thing that you have to define, but it directly follows from your definition of substitution. So once you have substitution implemented, you can just call that for alpha equivalence. Okay. So all we've done in this part of the lecture is we've just studied the syntax of lambda terms. We've studied a bunch of properties, right? We've studied substitutions. We've sort of looked at how to parse lambda terms. We've also defined what is the alpha equivalence. I've not actually told you the meaning. So even though I've been informally referring to this is what you get when you evaluate this term in an OCaml equivalent, we've not seen anything that has to do with semantics, right? Again, so as I mentioned in one of the first classes, right, we are going to study the syntax. Sorry, we are going to study the semantics, and every expression has a semantics and a syntax. And all we've studied so far is the syntax of lambda calculus. We will study semantics of lambda calculus now, right, in the next lecture. From now on, right, so unless otherwise stated, when I say, when we say lambda calculus terms are being equal, we sort of intuitively mean alpha equivalent, right? So when I say lambda xx is the same as lambda yy, I mean they are the same up to alpha equivalence, right? So both are identity functions. So it doesn't matter what variable name that I give. So this is the convention that we will use. Okay, so that concludes the syntax lecture. I'll pause for a minute, right? So I know there will be a bunch of things that you don't understand here. But if you have any easy questions, I can answer. If you have difficult questions, I will say, go browse through the material and come back and ask me the difficult questions after you've had a chance to look at this. Because otherwise, I'll just be repeating what I've just said. So do you have any easy questions? You can ask me questions. I'll just say that is a difficult question, and I can't answer it right now. Wait for a minute. Okay, so it looks like all the questions happen to be difficult questions. So I am available. Okay, so why did we need free variable introduction as a rule? Are we using free variables anywhere in the final inference rule? Yes, right. The substitution implicitly depends on good question. So I think Srisha is sort of asking a really good question. So because we are always okay, so let me try to understand. I think Srisha is asking a really nice question. I have an answer to that. Let me just try to put it in a form where I don't say something wrong. Okay, so you're right, Srisha. So we looked at a form of substitution that deals with a lot of complexity, right? In particular, it is looking at um, terms which are arbitrary, right? It is not just variables, but if you sort of look at, I really like the question. So, okay, so let me try to go back and open it up. So what Srisha is asking is, so you've told me all about substitutions. You've made us sit through this complicated rules, right? But it appears that is it not working? Very bad. Let me try again. Okay. So it appears that you're not actually using all of the complexity, right? So because we are using fresh variables here, right? The fact that I introduced this rule for free variables is not even needed because the variable that I'm substituting is always fresh, right? And the reason why I introduced substitution in its full complexity is that we will be using that for studying the semantics. That's a short answer, Srisha. But you're absolutely right. So we don't need this level of complexity for defining alpha equivalence. I would recommend sort of thinking about, because we always create a fresh variable z here, what rules can you drop from this final set of rules, right? And still have it work. Think about it offline. But to answer your question, yes, we need the full power of substitution because that is how I am going to explain the meaning of lambda terms. Okay, so and that's precisely what we will study in this next lecture. Really good question, Srisha. Okay, so that nicely leads on to the next lecture where we studied syntax. We are now going to study semantics. In particular, we are going to look at reductions, and reduction you can also read it as evaluation. So what does it mean to evaluate lambda calculus terms? We will see a bunch of theorems, but I'm just going to state the theorem but not go through the proof because I think the proof is not proof is firstly tricky but also not useful, but you will intuitively see that why the theorem should hold. Okay, so what we have seen so far is alpha equivalence, right? That's the thing that we've seen, and we are using substitution as a proxy for defining alpha equivalence. The next thing we have in the study of lambda calculus is this idea known as beta reduction. Beta reduction, you can sort of think about that as what happens when I actually run my program, right? Oh, you've written your program, you've told me so many things about the program being equivalent. I actually want to run the program. What does it mean to run the program and get to a value, right? And that is beta reduction, right? And so far, the lambda calculus that we've been looking at is untyped, right? There are no types here, unlike OCaml. So there is no static semantics. There is no type checking, right? There is only dynamic semantics. The only semantics that you have for a lambda term is what happens when you evaluate it, right? That's the dynamic semantics, right? So I will introduce a few terms, but I will also touch upon all of these terms in the rest of the lecture. So thing that we are going to look at is beta reduction, right? And the form this where you have lambda x dot m applied to n is called a beta redux. And why is it called a beta redux? It is the application, right, where the left hand side it is going to be a lambda abstraction, and the right hand side is an arbitrary term. We don't care about that. So we can actually perform the reduction, right? So this is like saying, oh, you have fun x arrow 20, and I'm applying it to 10. I can now reduce it to 20, right? Because it's a constant function. I'm applying it to 10, it ignores x and it returns 20. That is the intuitive meaning of beta reduction. And the form that we have here, when you have a lambda x dot m applied to n, we call it a beta redux, right? And how do we explain reduction? We just perform substitution. All we do is we just perform substitution, right? So if you have a lambda x dot m and then an n, the act of reducing, evaluating this lambda term is wherever you find x in m, replace that with n. So the way to read this is replace n for x in m, right? The beta reduction step of this term, applying this term, is really performing just substitution. So if you keep doing this repeatedly, you will encounter some form. If you can keep doing this, right, keep doing this substitution, go on doing it, but at some point you will sort of finish, right? At some point you may not be able to apply this rule anymore. And when you come to such a position, right, we call that lambda term, the last lambda term that we have, as the beta normal form. So in OCaml, this would just be a value, right? You have some you have some expression which you're reducing and it reduces to a value. So this is precisely that. Raghu Raman has a question, sir. Shouldn't it be n? No, right? So we are. So this is the body of the expression, right? So this is like fun x 20, and this is going to be say 10, and the result of fun x arrow 20 applied to 10 is always 20, right? Because you have a constant function, and that's the argument that you're ignoring. So it should be the term m on the outside, right? And wherever you have x in the term, you replace that with n. And in fun x arrow 20, there are no x's, right? Because fun x arrow 20 just ignores the argument. So n, which is 10 here, is just ignored. Okay. Yeah, okay. So continuing on. So here is beta reduction formally, right? So again, we are using inference rules, right? So we have a conclusion, we have premises, and the way to read this is there are 4 equally applicable rules, right? So there is no order between the rules. You can apply this in any order, as long as it's like pattern matching, right? But unlike pattern matching in OCaml, which proceeds from top to bottom, these rules are equally applicable. So if your pattern matches, if the lambda term that you have matches the pattern, any of these patterns on the left of the arrow, right? This pattern or these patterns, you can always go to the next pattern, right? The pattern to the right of the arrow, if the premise holds, right? If the premise holds. So okay, so with that, what is the rule for actually evaluating lambda expressions? So if you have a beta redux, right? So where I say lambda x dot m applied to n, this is what we saw just now. Just substitute in m, n wherever x appears, right? In m, substitute n wherever x appears. and that has no premises. So you can just, if you see this term, you can just always take a step. And we write this arrow beta just to say that it's a beta reduction, right? Because it's reducing, you can sort of imagine writing arrow, 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 and so on. So let's ignore this for now. Let's look at these two rules. These two rules are sort of simple. They say if you have an application, right, and you can reduce the first step of the application, the left-hand side argument of the application one step, then you can reduce the whole thing one step to m prime n. So if you can go from, consider you have mn, and you can go from m to m prime, then this whole expression can go from mn to m prime n prime. And in the same way, you can also do it for n, right? So consider you have mn. If you can go from n to n prime, then you can go from mn to mn prime. So all of these are equally applicable. And the last rule is says how to reduce within the body of an abstraction, right? So lambda x dot m, if you have this term and you can go from m to m prime, then you can go from lambda x dot m to lambda x dot m prime. So if you sort of put your OCaml hat on, this rule looks weird, right? So this rule sort of says, what is the OCaml equivalent of this term, right? So if you have, say, lambda x dot 10 plus 10, it says that you can go ahead and reduce the body of the lambda expression to 20, right? But as we have seen in OCaml, when you write such an expression, lambda x 10 plus 10, OCaml does not evaluate it, right? Because functions are considered to be values. Here we are actually reducing within the body of the abstraction, if possible. So maybe that example was not obvious, but imagine an example where you say fun x arrow print string hello world, right? That fun x arrow print string hello world is an abstraction, right? In OCaml, unless you call that function, the print string will not happen. But this particular form of reduction says you can go ahead and reduce within the body of the lambda expression. It's a bit strange because we are studying this idealized language, right? So, but this happens to be useful. So we'll see why. Okay, so the point that you have to sort of take care is this is a bit strange, right? I just remember that we are actually reducing within the body of a lambda abstraction. In OCaml, when you just write funx arrow e is not reduced unless you apply this function, right? Unless you actually have a value for x. Doesn't matter whether this x is used or not. Unless you have a value for x, when you actually apply it, you won't evaluate e, right? But we are evaluating m here. So here is an example. Yeah, so mn, Venkat Rahul has a question. In mn, m has to be of type lambda. We only have lambdas, right? So it doesn't matter. There is no type, right? So it can be anything. It can be, yeah. It can. We don't have constants also, right? This is a bit, yeah. So you're asking really good questions. We don't have anything else except lambda. So yes, you okay. So let me rephrase your question. Can it be a variable? Yes, it can just be a variable, right? So it can be a free variable. So the whole lambda term could just be f applied to some complex lambda expression, right? We don't know what f is, but you can keep reducing the n term, right? I think some of this will become clear once we start looking at examples. So the thing to remember, Venkat, is that we don't have constants. We only have one kind of value. It's a bit strange, right? This is very, very Spartan, this language is. So you have to sort of, one thing that allows, one thing that sort of, the thing that you learn by studying lambda calculus is you sort of shed all of these preconceived notions of what a language should have, right? This is like reaching nirvana, right? Throw away all your desires about what a language should have. Study the fundamental things so that you know what constitutes the core of programming, essentially. We are studying something that is equivalent to a Turing machine, right? But we are studying it in a programmatic setting. But once you sort of throw away all that, some of the concepts become much easier. And as you keep adding more and more stuff on top, because you've studied the core, um, you will hopefully see through the patterns, right? You will hopefully see through the craft. So let's look at a few examples. I think this will sort of guide you towards what is happening. So here is this term. The thing that I've highlighted with yellow is what I'm reducing. So the original term is lambda x xx applied to lambda x dot y applied to lambda z, right? So this whole term. So the thing that I'm highlighting is what term am I substituting for what other term, right? Those two are the thing that I've highlighted. So here I've chosen to substitute for x this whole term here, right? I can do one step of beta reduction. Because the body of the term is xx, this term is duplicated twice, right? You, wherever x occurs here, replace this whole term. So whole term once and this whole term again, because for this x. And then you can choose to reduce these two terms. Wherever you have x in this term, substitute that with z. We don't have an x, it's a constant function, right? So this will just be y. And similarly, the same thing for the second one. And what you end up with is just yy, right? And that's, we don't have any other further possibility of evaluating this term, right? So we just call it as a term that is in beta normal form, right? So this is one way of reducing it. As I mentioned earlier, you can apply these rules in any particular order, right? I can either reduce the function argument or the value argument, right? Because this one is reducing the function argument, this is reducing the value argument. And similarly, you can also do other ways of reducing it. Here I first reduce the usual first term, right? So the outermost term. So I get the term replicated twice because I am applying x to x here. Then instead of reducing the function argument, I'm actually reducing the value argument. So this returns y. So this becomes y here. And then I reduce this term. So I get yy. The thing that you need to sort of keep track of is I'm always arriving at yy, right? And this is also yy. You can also do something else, right? You can reduce, instead of reducing the outermost term, you can reduce the value argument in the first term. Good question, Venkat. So how do we interpret yy? There is no interpretation. So it's just yy. So just go with the semantics for now, right? It is yy, just yy, right? So in the next lecture, we will actually see what does it mean to add meanings on top of these lambda terms. We will actually start with things like encoding Boolean values, encoding integers from scratch. We will actually build up integers, right? Imagine a world where you did not have integers at all. We will use lambda calculus to build integers. It's a fun exploration. It's like a puzzle. So we can ask about what an interpretation of a term means when we study that. But now we are just looking at how do we evaluate terms, right? Okay. So with that, you can also reduce it in a different way. You can apply, you can reduce the rightmost term, right, which just gets the constant y, and now you get yy again. So the rule that is defined here, right, is defining a single step of beta reduction. So this is how you take a single step. And if you look at the examples, I'm taking multiple steps, right? So I can define this helpful meta definition, which is just multiple steps of beta reduction. right? Which just says I can go from the lambda term m to m prime in multiple steps of beta reduction if I can go from m to m prime in one step and m prime to m double prime in multiple steps. So this is if you study transitive relations, right? This is precisely the definition of one definition of how you define transitivity. So if you want to go from, if you think about walking down a linked list, how do you go from some starting node to all the way to the end? If you can take a step to the second node and you can take a step all the way to the node that you are interested in, then you can traverse the path from the first node to the node that you're interested in, right? So that's the definition here. And we also add this other definition, right, which says that in particular, we say that you can go from m to m prime using multiple steps of beta reduction if m and m prime are alpha equivalent. So this seems a bit strange, but we are just saying that ignore just take into account that the terms might be alpha equivalent, right? So that's really what we are saying here. So it doesn't matter if you end up with lambda x dot x or lambda y dot y. Just consider them to be the same thing as reached by multiple steps of beta reduction star. So why did I define this particular relation? I am using this relation to express Church-Rosser theorem. So it is an interesting observation. So what we saw in those three examples is whatever way you choose to reduce the expression, you will always arrive at the same final redux, right? So this is the example. So one way to go down is this is the first way to go down, right? We started from lambda x this term. We duplicated the two terms and then we evaluated the left. Sorry, this is evaluating the right one, and then went to yy. This is evaluating the function argument, right? Then went to iy. This is first evaluating this term, got y, and then you substitute, you get yy again. Church-Rosser theorem says that this holds for all lambda terms, right? And it says that if you start from some term m, and in multiple steps you go to m1, and you start from m, and multiple steps you go to m2, right? Some other m2, then there exists an m prime such that you can go from m1 and m2 to this m prime. So all it says is if you go down some distance, yeah, so then you can always go to the same term by multiple steps of beta reduction, right? So this is quite nice because it doesn't matter which way you reduce, right? So that's really what Church-Rosser theorem is saying. We're not going to look at the proof, but this is a nice observation. This has been proved. Again, so beta normal form. We briefly mentioned beta normal form. What is beta normal form? It doesn't contain any reduxes, so you cannot reduce it anymore, right? So an example of a beta normal form is this one. There is no way to reduce this term, right? So we say we've reached a beta normal form, and thanks to Church-Rosser theorem, we have the property that if you reach a beta normal form, right, then the beta normal form is unique. So if you start from some lambda term, right, m, you go to n1, and you start from m, you go to n2. Assume that n1 and n2 are in beta normal form. Then the theorem says that n1 is alpha equivalent to n2. They're both the same terms, right? So why is this true? You can directly apply Church-Rosser theorem here. So obtain an n such that you can go from this n1 and n2 to some n, right? n1 to n and n2 to n. But we know that both the n1 and n2 are in beta normal form, right? According to the theorem statement, and which means that you couldn't reduce it anymore. So it must be the case that these two are alpha equivalent. All of these are alpha equivalent indeed. So the intuitive meaning of this is saying if you take a program, right? If you take a program that is in lambda calculus, you choose whatever way you reduce it, you will always arrive at the same result. if you arrive at a beta normal form. That's quite important here. Yeah, so the last thing which we will see before looking at further examples is this idea of beta equivalence. We looked at alpha equivalence, right? What is alpha equivalence? I give you two terms. These two terms are alpha equivalent if you can go from one term to the other just by renaming. Here, beta equivalence says that can you give an example of a pair of M and M prime which are alpha equivalent and the steps of beta reduction between them? So we can, so if you have a, you can just take the same term, right? So you can just take lambda xx, lambda xx. Both of these terms are alpha equivalent. And the steps of beta reduction is we are applying this rule. We are sort of resorting to this rule. If two terms are alpha equivalent, we're just calling it as being able to go from M to M prime in multiple steps of beta reduction. It's a bit weird. I should have really named it as something else. But if two terms are alpha equivalent, I just call them to be the same as going from one term to the other. Yeah, that's the definition. That's the definition that we are going for. So this beta star, right? I'm sort of defining it as multiple steps of beta reduction. But you can just think about some x, right? Multiple steps of some x. And that step includes alpha. That step includes transitivity. The step also includes alpha equivalence. Yeah, that's the definition. And we need it because I mean, I don't have an example in hand, but if you choose to see, here is the intuitive reason why we might end up with two alpha equivalent terms, right? Recall how we did this freshness, right? I just told you pick a fresh variable which the world has never seen before, right? Now, if you have two branches, two ways of evaluating something, the fresh variable that is chosen here might be different from the fresh variable that is chosen on the other side, right? And then you will end up with something that looks like, say, lambda x dot y, lambda x dot 0 and lambda y dot 0. These two terms are the same up to alpha equivalence, right? Because the meaning of those terms are the same because we are anyway ignoring x and y. Lambda x dot 0 and lambda y dot 0 happen to be different because the freshness gave us two different variable names. And that's the reason why we include alpha equivalence there. Yeah, hopefully that will have clarified what is this evaluate to. So this evaluates to, so you have a term which is lambda xxx applied to lambda xyz. Is that right? Or is it, how do I interpret this one? This is this lambda x dot x applied to x applied to lambda x dot yz. That's how I should read it, right? What I'm asking is this. Without brackets, you cannot reduce anything, right? Because let me try to write it down here. So you have this one, right? So the bracket goes from here to here, right? And there's a bracket from here to here. In particular, you can also add a helpful bracket here, right? If you remove this one, it is this, right? So you need to first apply, you take an x, you first apply x to x, and then on the result, apply this term. This is not something that is reducible. Okay. Yeah, so if you had asked me something else, right? If you had asked me something like this, that's an easier one. Okay, so this is just yeah, okay. So in order to ask all of these questions, right? There is so let me just finish this. What I was saying. So here is a more intuitive way of explaining all of this, right? So if you have fun successor function defined as fun x arrow x plus 1 and fun y arrow y plus 1, applied to both of these functions applied to one, then these two functions are alpha equivalent, right? You can rename this to z, and you can rename this to z. They will be the same terms. They are also beta equivalent, right? So they reduce to the same value. This reduces to 2, and this also reduces to 2, right? And here is a term, the same term as this one, right? But on the right hand side, I have one identity function applied to 2. These two terms are beta equivalent because both of them reduce to 2, but they are not alpha equivalent, right? Because you cannot go from one to the other by just renaming. So this is sort of what we are capturing with all of the complexity of this formal notation. Okay. Yeah, okay. So I'll stop here. I'm already 5 minutes over time. There is, I think there is an evaluator. If you want to see how things evaluate too, we will come to this evaluator in the next class. You can play around with it. Any questions that you might have, just you can type in this evaluator and it will tell you each step of the reduction. We'll look at it in the next class. I'll stop here. Thank you very much.